Okay, welcome to one of my most favorite topics of them all, astronomy and cosmology. And in this video series, we're going to be exploring all the different aspects that fall underneath this topic. So to kick off, we're going to understand a lot of different objectives. And if you need access to this document, you can always access it in the description below. So to start off, we want to understand what exactly is astronomy and cosmology to begin with. So this is a topic that best explores astronomical objects. This ranges from planets, moons, galaxies, and all of these bodies and how they interact. So we're going to start off with luminosity. So first of all, we start from a star, right? Astronomy, we start from a star. So basically a star is a ball of gas that emits radiation as nuclear processes occur. So luminosity is a particular concept that revolves around understanding what I just said. So luminosity, if you're to define it, if you have notes, write this down so that you're able to understand. But luminosity basically refers to the total power output of radiation that is emitted by a star. So if you have a star like this, it's going to emit out light or radiation in multiple different directions. And luminosity is basically trying to understand what is the total radiation that is emitted by that star, right? But if you're an observer, you know that the sun is going to emit some light, right? But you want to observe it on Earth. So what you're going to do is we're going to introduce a concept known as radiant flux intensity. Radiant flux intensity basically refers to the observed luminosity or radiant power that is transmitted through a surface area. I know I said a lot of things. What do I mean by this? Okay, so assume you have a fire. You have a fire and you put it over there. The amount of heat that is hitting square meter of skin is going to be radiant flux intensity. So the amount of energy hitting 1 square meter of skin per second is what we refer to as radiant flux intensity. Why is this important? Because if you can measure that, you can be able to determine the luminosity of a star if you know the surface area of the star, right? So essentially, how much energy is passing through a surface per second is basically what we refer to as radiant flux intensity. So we have an equation that connects the two, radiant flux intensity and luminosity. And the whole goal of astronomy and cosmology is just understand how these bodies work. And we started off by understanding what a star is, and it's just a ball of gas that emits radiation that is known as luminosity, right? Luminosity measures the power that the star emits. And we also understood that if you're an observer, you can also be able to measure the amount of energy you're getting per second on 1 square meter. And that's basically known as radiant flux intensity. So an equation that connects the two can be found as follows. So imagine you have a star in the sky that is emitting energy in all directions, north, east, south, west, all of that, like a perfectly glowing sphere. Now let's assume, right, as this energy starts to spread out, it fills an imaginary sphere around this star. So this is basically an imaginary sphere that it fills as the energy spreads and spreads out, right? So we want to figure out what's the total area that this energy is going to spread over. So the equation of a sphere is basically 4 pi r squared. This is something that you just know, right? Like the volume of a sphere, for example, right? So the energy that is being released is being spread over that area itself. Now, therefore, the total distance r, the amount of energy will be spread over the surface area 4 pi r squared. Now, you can easily therefore find the energy per unit area because you have the total energy being emitted. That's luminosity per second. You have the total area itself, that's 4 pi r squared. Divide the two and you're able to calculate radiant flux intensity, right? A little bit of a mistake here. This is supposed to be radiant flux intensity. Okay, so it's measured in watts per square meter. Luminosity is measured in watts, and then R is the distance that is measured in meters. Okay, so the equation itself, therefore, just assumes that the power from the sun radiates, or from the star, radiates uniformly through space. That is going to form this little perfect sphere, which in reality, it might not even be something that's happening. Another assumption that we make is that there's no radiation absorbed between the star and the Earth. So if you're assuming that this is the star, for example, and we assume that the Earth is somewhere over here, our assumption is that all the energy released by the star is essentially going to hit the Earth, which in reality might not actually happen. So we can therefore safely say that radiant flux intensity follows what is known as the inverse square law, which we've already discussed and studied in the topic of gravitational fields. So the further you move away from a source, the weaker the strength will be. As you can see here, if you're closer here, you're going to have a very, very strong, luminosity. You're going to have very strong light or radiation that you're experiencing over that area. But the bigger the area gets, the weaker it becomes because it's a larger area, right? You can't expect to have the same amount of energy per square meter if you have a larger area where that energy is spread over, right? So that's basically it. That's basically all you need to know about luminosity and radiant flux intensity. And I'll meet you in the next video. We'll solve a couple of examples around luminosity and radiant flux intensity.